So we're basically done with our discussions of parallel streams for the time being. You'll be applying them, of course, in the programming assignment 1B, and I'll give you your feedback on that shortly. But what I want to do to kind of wrap up the discussion is to talk about when you should use parallel streams, and then the next video we'll talk about when not to use parallel streams. So first we'll talk about when you should use them. So the first thing to note is that parallelism is not a panacea, right? It's not a cure-all for everything that ails you. A parallel program will always do more work than a non-parallel program. In particular, it needs to partition the overall task, the original data source, up into subtasks, so that takes some time to split things. And then, of course, it needs to process all the subtasks in parallel, and that's typically what all you would do in a sequential program. In a sequential program, you just do work. You wouldn't have to split, for example. And then the final thing you have to do is you have to take the sub-results of the subtask results and combine them together. So if you think about it, steps 1 and 3 are extra. Those are not done by a sequential program. Therefore, you really better get your bang for your buck for step 2. Otherwise, all this splitting and combining or splitting and merging is going to be for naught. You're not going to get a win. And you've already seen some examples of when you don't get much of a win, right? And we'll talk about that in a second. So Java parallel streams are therefore useful in some, but certainly not all conditions. So you have to think it through. And there's a nice article here by my friend and colleague Doug Lee, based on some work with the parallel streams working group in the Java process, and it talks about some guidance for when to use parallel streams. I'm going to summarize some of the stuff that's in that article. So Java parallel streams are most useful under certain conditions. In particular, when behaviors that you pass in have certain characteristics. One characteristic is they are independent. So if you recall our discussion before about so-called embarrassingly parallel programs, where we have little or no dependencies between the tasks, things work great then. And of course, the canonical example of this is the loads of laundry at the laundromat, where if you run them all in parallel, then you can get a huge speed up because your one set of load of laundry does not depend on the results from the other. A good example that we've seen multiple times is searching for phrases in a list of input strings. I think we'll all agree that's a nice example of embarrassingly parallel processing. And there's a whole slew of examples in my Search Stream Gang program that will show you how to do this kind of stuff. And if you take a look at this link, you can download and play around with that. The most aggressive version, which we actually haven't talked about yet, but we will come back to if there's time, we'll search each phrase in parallel and search each input string in parallel and search chunks of each input string in parallel. So you can really just go completely off the deep end and do parallelism in all kinds of dimensions. And if you do all 3 of them, then you typically get the best performance. Now that takes a little bit of extra work, but the good news is you can really squeeze out maximal performance in that case. Another situation where parallelism is a win is when the computations that you do are computationally expensive. In other words, they spend a lot of time doing processing. This is the Q in the n times Q model. So n is obviously the number of elements. Q is the amount of time you spend on each one, the quantity of time you spend on each one. And the longer that time is, the bigger the bang you get for using parallel processing. And of course, we want to apply them to many data elements. So if you have many data elements in your data source, then you're going to get a bigger win. Imagine if you had to, polish the terracotta warriors, right? And there was one of you. It would take you forever. But if you had, 100 people, they would be able to polish those terracotta warriors much more quickly because there's a lot of them. So n is large, and conceivably polishing them would take a while as well. Assuming that you actually polish a terracotta warrior. You may not actually polish it, but I'm not sure. I've always wanted to go see that. It sounds really cool. And this many element application model works extremely well if you can split your data sources efficiently and evenly. So like array lists are a big win relative to linked lists, for example. And this is what yields the so-called n times Q model that Brian Getz talks about. You can watch his video here where he talks about this. So n is the number of data elements to process, and Q is how CPU intensive the processing is. It's a quantification of how long processing is. So if n and q are big, then you're in the zone where parallel processing or parallel streams will help you out. So as we saw before, searching for phrases that match in the works of Shakespeare. That's a good example where there's a fair amount of processing time to match each phrase, and there's a large number of phrases, and there's a large number of input, so N and Q are big. Another kind of obvious situation where parallel processing is a win is when there are multiple cores. This may seem sort of obvious, but sometimes it's not so obvious. You can get a little win from parallel processing if you have one core, if you have the ability to overlap computation and communication, say through direct memory access features in your hardware. But you're much better off using multiple cores, and everybody has multiple cores nowadays, so it's not too hard to make that work. So under the right conditions, N times Q, independent tasks, etc., multi-core processors, you can get a nice speed up of parallel processing relative to sequential processing. So as we see here, we get like an N-fold speed up, where N is the number of cores, by using parallel processing. So that's a quick overview of when to use Java parallel streams.